Good afternoon and welcome to this new webinar in the CCAM series, The Importance of Being H.P.C. Earnest. So as you may know by now, the goal of this series is to explore, with the help of leading experts in simulation and modeling, the interest of being up to speed and ready to exploit high-end H.P.C. capability in different areas of our science. So today we continue this journey with three outstanding experts, Cecilia Clementi, Ignacio Pagona-Barraga, and Peter Coveney, who belong to different, slightly different specific areas of simulation and modeling. And this is in the spirit of CCAM, of trying to bring together people who may be in the same general community, but may not have that many opportunities to exchange, although, of course, this is one of the goals of what we do. So I don't want to steal too much time before we actually get to the presentations. Let me just remind you of a couple of things. This is a webinar, but it is a CCAM webinar. And so we care about all the things that we usually care about at CCAM. And in particular, we would like these webinars to be as interactive as possible. Now, being interactive with an online event is not as easy as interacting when you're sharing a coffee in the Karl Moser room. But we do ask you to participate by asking questions using the chat on this YouTube channel. Just log in if you have a Google account or a YouTube account and ask questions through the chat. If you don't have an account or you don't want to use it, you can still ask questions by sending an email to director@ccam.org. Please feel free to ask questions at any time. I will do my best to keep track of all your input throughout this webinar, and I will relay, with Ignacio's help, questions to our speakers at the end of the three talks. So it is a great pleasure for me to start this series, this particular webinar with Cecilia Clementi. Cecilia is an excellent example of someone who has expertise about the way in which simulation and modeling happen both in Europe and in the United States. She has recently moved from Rice University in Houston, Texas to Berlin, very recently, and it must have been quite an adventure making a transatlantic move during the COVID crisis. So thank you very much for being here, Cecilia. Her area of expertise is in the domain of protein dynamics, and in general simulations to characterize complexes with biological functions. She is also the co-director of an institute for software development in sciences funded by the National Science Foundation, US government. So the institute is called MOLSI, and I am really looking forward to listening to her views on various aspects to address outstanding scientific challenges in molecular sciences exploiting H.P.C. Cecilia, the floor is yours.
Thank you, Sarah. Let me share my screen. Do I do this? I think it is. Okay, tells me that Zoom cannot record because I just changed the permission. Zoom cannot record my content until I quit, but I'll ignore that. Can you see my screen?
Yes, we can.
Okay. So, as Sarah said, I recently moved to Berlin. I'm a professor of physics at Freie Universität. I was at Rice University before, and I'm also the co-director of the Molecular Sciences Software Institute. And today, I'll mostly talk about the role of the Molecular Science Software Institute in addressing scientific challenges in especially molecular sciences. And I would like also to invite you to interact with the Molecular Science Software Institute, or MOLSI, as I hope will become clear during my talk. But before I start talking about MOLC, I want to say something about my own research. I mostly focus on the modeling of protein and macromolecular systems at multiple resolutions, from atomistic to system level, for instance, cellular level, but mostly at coarse grain and multi-resolution. And we have developed multiple methods during the years to address multiple resolutions, and this is just a sample of a few papers. Particularly interested in coarse graining. I've been working on coarse graining for more than 20 years, and this is just a sample of the tools that we have developed and we use. And one particular thing that we also, this ODEM here is a framework to incorporate experimental data into coarse grain model that we are also developing now. I'm particularly interested, these are some applications of our technologies to different problems, mostly protein dynamics, functional roles in different systems, folding dynamics, misfolding, aggregation, dynamical changes, and so on. What I'm particularly interested recently is the developing of these models, these reduced resolution models, by means of machine learning, because I think machine learning is the perfect tool to for these models, because these models are very complex, nonlinear, and multi-body. And so it's very difficult to write an energy function analytically that can express these properties, but machine learning can come to the rescue. And with the neural network, or for instance, a Gaussian process, we can express these complex functions and do a much better job in developing coarse resolution models that are also very accurate. And these are some of the recent publications. And if you're interested in knowing more, please contact me. I'm hiring PhD student and postdoc in Berlin. So shameless advertisement. If you're interested, please contact me. But today I want to talk about the Molecular Science Software Institute and this role, the role of MOLC in advancing science in high-performance computing and high-performance computing. What is it, and what I mean by advancing science? So there are several problems in science, outstanding challenges that require software solutions that do not exist. Even if we have the most powerful computers, we need to have the software to say something about the science. Let me give you some examples. One example is understanding structure function of intrinsically disordered proteins. We need new software, or we need a different use of existing software, I would say, to understand something about intrinsically disordered proteins. Why? First of all, intrinsically disordered proteins are a relatively new area of structural biology, structural biochemistry. They are very abundant. 25% of proteins do not have a fixed structure, three-dimensional structure determined by the sequence. The central dogma of molecular biology states that a sequence determines the structure, determines the function, but these proteins defy this dogma because they have a well-defined sequence, but do not have a well-defined structure. They're very dynamical objects. They change configurations, but they have a function, and they're actually very important for cell regulation and signaling. They can fold while interacting, while associating, while binding. And so the time scale on the function, for the function of these proteins are pretty long because they require folding and interaction and so on, and dynamical changes. Experimentally, they're extremely challenging because they are very dynamic. So you cannot use X-ray or NMR as usual. I mean, you can do something, but you cannot use these tools as you do in structural biology, in normal structural biology. So computation is extremely important to say something and fill the gap in experiments. But we need high throughput computation, high performance computing. These computations are very challenging, but also we need new software because we need new models, for instance, because most of the force fields and the potential energy surfaces that exist have been developed for proteins, have been developed on the protein data bank on a folded proteins, and these proteins are unfolded. So there is a bias in the existing force fields for folded proteins. They need to be corrected. We need very aggressive samplings for the extremely large configurational space explored by these proteins and the long time scale for their configurations. We need new models and also new codes. And we need to combine different codes. Some codes are maybe good for sampling, some codes may be good for analysis, and they need to talk to each other. So interoperability is an important thing, and I'll stress it in the next few slides too. We may have components of the software available, but the pieces of software do not talk to each other. So it's very important to try to fill the gaps in the software solutions existing. Another area that need new software solution is the design of catalysts at the molecular level. The performance, optimizing the performance of catalyst is, of course, I don't need to convince you, extremely important. It's very important for many very practical applications, for instance, for energy, for industry. And the parameter space for the optimization of catalyst is too large. You cannot just try experimentally all the possible combinations to try to find a better catalyst. You need computation to understand at the molecular level the mechanism of the catalysis to design better catalyst. And again, you may need different pieces of software because you need quantum mechanics, but you also need dynamics. So you need sampling, you need models at different resolutions, and different groups may have different parts of the solution, but you need to put things together. You need some software framework that combines different expertises. Another area is complex material chemistry. Again, by complex material chemistry, I mean chemistry or material science that requires complex physics, that requires, that spans different areas of science. For instance, electronic structure, non-equilibrium, dynamics, statistical mechanics, equilibrium, non-equilibrium, statistical mechanics. That means electronic structures codes, statistical mechanics, sampling codes, non-equilibrium tools, and so on. And again, we need software for this. Again, we need interoperability between different pieces of software. We need to combine different solutions. And or another example is the assignment of a nonlinear optical spectroscopy solution. In order to understand the structures, you need to run sophisticated simulations of nonlinear spectroscopies, and you need to sample the solvent around the structures because these more intermolecular interactions are very sensitive. And again, you need a combination of state-of-the-art dynamics and electronic structure approaches. And these combinations do not exist. So for this, we created MOLSI, the Molecular Science Software Institute. MOLSI exists since 2016. It's funded by the National Science Foundations in the United States, and is a collaborative effort of 8 different institutions. It started when I was at Rice University, and we are 8 people as co-director and co-directors, and each of us is in a different institution. It's part of the White House National Strategic Computing Initiative. We have quite a big budget, And next year we are up for renewal. So we have been running for 4 years. Next year will be the 5th year. We will try to go for 10 years. The idea of the MOLC is not to have another research group competing with existing groups in designing new software. We want to serve the molecular science community to create software solutions enhancing what's available. And I'll try to explain this in the rest of the talk. So we want, first of all, by molecular science, I mean everything that molecular software at the molecular science level. I mean every piece of software that deals with computing molecular properties like quantum chemistry, computational material science, biomolecular simulation, biophysics, molecular dynamics, quantum chemistry, and so on. And we are in practice. It's MOLC is composed by a dozen of software scientists. These are PhDs in either chemistry, physics, applied mathematics, computer science, a very interdisciplinary group of people, very solid people in terms of science and scientific achievement, but also very expert software engineers. They are a rare combination of expertise in computational molecular science and in the software aspect of it. In addition to the software scientists who actually do the work, who perform the software engineering component of MOLC, that is the main part, we have software fellows. That means that we support graduate students and postdocs in individual research groups across the United States for bridging the work of the research groups into into purporting the research group, the work of the singular research group into some general software ecosystem that is interoperable and with good practices and so on. So this is a way to enable research groups to design software solutions that are more general and more interoperable than what's existing right now. Also, another important thing about the software fellows is that most students and postdocs working in molecular science are not trained as software engineers, are trained as physicists or chemists. And that's good because this is the science they want to address is in physics and chemistry. But in order to solve the science questions, you need the software and you need the expertise to design the software. And so these fellowships allow the software fellows to gain this expertise by interacting with the software scientists. And also it's very difficult to find the financial support for software in a research group. I think all of us had this experience. You have an idea and you can find support for an idea from a government agency, a private foundation, but it's very difficult to find the money to support the software for the practical application of the idea. So these fellowships give the means of supporting software solution. We are 8 co-directors that we oversee the activities and provide the guidance to the software scientists. We decide the direction, basically. We have an advisory board that is changed quite often, every 1 or 2 years. And we involve representatives from academia, industry, national laboratories, international, not just in the United States. And this is to decide the software priorities and also to assign the software fellowships. The software fellowships are decided by the advisory board. And we interact with the community. So The projects, I'll say something about the projects later. The projects are determined by the community needs. So we had over the years many groups approaching us with the problem or with an idea for a project, and we asked to submit a short proposal, and then we discussed it informally, and then we started different projects according to the request of the community. And I'll give some examples later. We work with community codes. So as I said, we don't want to create another code to compete with what's available. We don't want to create the next molecular dynamics code. There are enough of them, but we want them to work together. So this is a list of all the codes, community codes we interact with that are partner with us, and we encourage all the community codes to work with us. And for instance, the software fellows can come to us with an idea to port a new tool into one of these codes. And that is something we could support. But we need to make it with the requirement to make it as general as possible and interoperable and all of that. We have currently 12 software scientists, but we are hiring more. So if anybody, if you know people who may be interested in working mainly in software, but in science, this is a pretty good job. We run workshops. That means the workshops is our way to interrogate the community on what we can do, how can we help in terms of software solutions. The workshops are community driven, so we are the community, the different people apply, saying want to support the workshop on I don't know. We had recently a very successful one on machine learning. I would like to bring together machine learning and computational molecular sciences expert to interrogate the community and achieve a consensus on what's needed in terms of software solution for the emerging area of machine learning and chemistry. And that was a very successful workshop that, and you'll see we have some activity in machine learning that also resulted from that workshop. There is also important computational educational effort, because as I said, most people working in computational molecular sciences are physicists or chemists that are very solid in physics and chemistry, but are not formally educated in software. So we want to try to improve that, and we offer educational workshops, schools, boot camps, programming schools, and so on, to try to form the next generation of computational molecular scientists with the solid background in software development. And also another way to educate, to form the next generation is through the software fellowships that I already discussed. Over the years, we funded about 60 fellows. We have about a couple of dozens at the time. So the main goal is to provide the expertise and infrastructure. So we work with research groups in US and internationally to design, develop, test, deploy, and maintain code and infrastructure and frameworks, and to make different pieces of code that exist work together to try to achieve something that cannot be achieved with existing solutions. We interact not just with the single research groups, but also with industry, supercomputing centers. That is very important because most of these codes need to be deployed on supercomputing facilities, national laboratories, international facilities, and we keep an eye on emerging software solution, hardware solution, because we want the codes that are developed not just to be able to run on today's computer, but on tomorrow's computer as well. Otherwise, we need to rewrite the codes in a very short time to be able to better exploit the available hardware in 5-10 years. Although it's impossible to know what's going to be the best hardware in 10 years, but we can keep an eye on what's available next. And also we interact with all these different partners in order to understand the software priorities and what's important for the educational activities for career paths for the software scientists or the software fellows. Education already discussed, that is done through the software fellows, all the different workshops and activities, and also we have undergraduate training programs and also high school. We have also an outreach program. So most of the work is community-led, so is a grassroots approach. We want the community to tell us what are the software problems we need to address. We have 12 software scientists who are extremely capable people and are ready to work to help to serve the community to advance software. So it's very difficult, or not many research groups want to do some software work that may be extremely boring for a researcher who wants to get a PhD in physics, but it's needed. And nobody wants to spend 6 months or 1 year for a piece of software that may be extremely important, but is 6 months or 1 year of a PhD time. We can do that. MOLC can do that if it's important, if it serves an important science goal. So already discussed the different activities, and already said that we are 8 people. These are the faces of the 8 people. I am responsible for biomolecular simulation international engagement, and Daniel Crawford at Virginia Tech is the main director. Then we have a co-director for parallel computing and emerging technology. We have a director for academic outreach, laboratory industrial academic outreach and education. We have a director for software engineering processes, for quantum chemistry, and for code and data interoperability, and for material science. The software scientists are 50% of the budget, and they do the work. These are the people who do the work, or the people who write the code, they develop the software infrastructure and frameworks, and they interact with the community, and they serve as mentor to the software fellows, and so on. We have the software fellows that I already discussed, and this is 30% of the budget. And this is also a way to interact with the community. This is a main way to interact with the community, because the software fellows, as I said, are PhD and postdocs in individual research groups. These do not reside at MOLC, but they are pursuing their PhD or postdoctoral research, and as part of it, they get help on a software solution. The molecular software fellows have been extremely successful in finding jobs after their fellowship, or they received awards, they published paper, they have released a lot of code. So it seems the mechanism seems to work. This is a picture of the current software fellows, the new ones. We have some from last year. These are the newly appointed one this year. We had an interesting last few months, because everything was working fine as for everybody until COVID arrived. And we had to, as everybody, we had to switch to virtual mode, and we had to postpone all the workshops, and we had to move the education into webinars. But we asked ourselves, what can we do as a software institute to respond to this emergency. And we launched a new initiative very fast, that is the Molecular Structure Therapeutics Hub. And I'll say something in a second, but we also asked National Science Foundation for additional funding. We wrote a proposal very quickly, and we got another 200K that we spent in awarding additional software fellowships to address this specific problem, because molecular science is central to fight COVID. I mean, it's a virus, it's made of proteins. So we need to understand how they work, and we need to bring together the community to do that. We need to, it's such a big effort. We need many different research groups to work together to this. So we have launched, and we're putting together and maintaining this hub, covid-molc.org. You can check it out online. It's a way to share data, trajectories, structures, tools for COVID, for fighting COVID. So if a group runs a huge molecular dynamic simulation of a specific protein, for instance, we have data from the SHORE research. They have run very long molecular dynamic trajectories of different COVID-related proteins. We want the whole community to look at this data, to be able to mine this data and get something out of it. We don't want somebody else looking at the same protein to rerun the same simulation that was a heroic effort in the first place. So we are sharing, we're making this data available to everybody. And we encourage everybody who has anything on COVID to contact us so that we can upload the data. And we have resources, we have talked with different partners, so we have resources to host very large amount of data. So this is what we did very quickly in response to the COVID emergency. So we want again to enable the community to address the problem. We don't ourselves run a simulation, but we enable the community to work together to find a solution. The software infrastructure development is the main goal of MOLC, and we have several different projects ongoing. In order to decide if a software activity is going to be supported, we ask ourselves, is it enabling new science that cannot be addressed otherwise? This is the main criterion. Is this software needed to answer some scientific questions? For instance, the scientific questions I mentioned at the beginning. And another important component is it making existing software interoperable? Is it integrating existing software? We don't want to reinvent the wheel. If there are pieces of software that are available, we want to make it, we want to incorporate it and make it work together. This is a list of the ongoing projects. There are many, some of the software for some of them has already been released. Some are in progress, some are brand new. For instance, the COVID one is just started, as I just mentioned. There is, in this list, there is the molecular mechanics interoperability component that is focused on making the different molecular mechanics software talk to each other. There is the MMM schema, is to be able to share trajectories and make trajectories compatible with different softwares. There is the machine learning project. I'll say a few words later. There is the driver interface that is to be able to combine molecular dynamics and quantum chemistry software for different problems. I'll say a few words later. There is, for instance, this is one particular project, the Basisset Exchange, that is a new Basisset database that makes different Basisset compatible. You can transform it in different format, and is a huge database, and this has been very successful. Is a lot of visitors. It's already been released, so now it's in maintenance mode, and is widely used. Another thing I mentioned is the driver project, that is to simplify, standardize the interoperation of different codes on the fly. For instance, if you want to do QMMM, is the immediate application, but there are other important applications that require the interoperation of different software. There are different components. Is in beta since June. We are working with different engines. It's still under development. We'll extend it to other engines. The drivers that's been developed as proof of concept are QMMM, that is the immediate one, but also ab initio molecular dynamics, nudged elastic band, metadynamics. These are all different software solutions that require to use different packages, different codes, and we can make them interoperable on the fly. So we can share forces, coordinates, energies, and so on between different codes. Another very successful project that is in beta is the Quantum Chemistry Archive project. This is a huge database of quantum chemistry data. So it involves the evaluation and storage of quantum chemistry calculations. And it works across, it involves a very large number of groups and codes and cyber infrastructure and so on. I don't have time to go through it. If you're interested, I can tell you more. Another important thing is that this is done in collaboration with the Open Force Fields Consortium. That is an important, very large effort to compute the next generation of force fields with machine learning or with existing tools in order to obtain this new force field, very accurate force field. You need data. You need a lot of quantum chemistry data. You need to store this data. You need to make databases to retrieve this data efficiently. And this is what the Open Force Field Consortium, in cooperation with the Molecular Science and Software Institute, is doing in this respect. Machine learning, I mentioned, is an important effort. For machine learning, again, you need data. We have seen a lot of very important contributions where people have been designing very good force fields where the force field is not, the energy function is not an analytical expression, but is a neural network, for instance. But the neural network is trained on a huge amount of quantum chemistry data. And if a group is doing it and then is releasing the code, it's okay. But then if another group wants to improve it, it needs the data. And in order to have a comparable solution or to understand the performance, you need to use the same data, or at least the same data and augmented data. So we want to make the data available to everybody, again, to organize it, to collect them, organize them, and share them, and then be able to retrieve, organize them in databases and so on. And we think this is an important contribution for the next generation of machine learning-based force fields or chemistry tools. I think I've exhausted my time, so I want to acknowledge MOLC, the NSF who gives us the money, and all the members of the computational molecular science who are involved into this. It's a huge effort involving many different groups through the different activities, the software fellows, the feedback, the workshops, and so on. And this has been going on not just 4 years, but 8 years, because before the institute, we had a conceptualization of the institute where we started all these activities. And I also want to thank my research group. This is still the old website. I'm recently, as I said, at the Freie Universität Berlin. And I want to thank all of you for your attention. Thank you.
Thank you very much, Cecilia, for this very interesting talk and description of a truly impressive initiative. I'm sure it's going to be interesting to discuss it in the question and answer session. So please, anybody who is curious about anything that Cecilia has just described, ask your questions through the chat on the YouTube channel or by sending an email to director@cicam.org. So now we're going to move to the second speaker of today's program, who in principle shouldn't need much of an introduction to the CICAM usual audience, because we are talking about Ignacio Pagona Barraga, who is the current CICAM director. Now, in his spare time from this activity, Ignacio is also an expert in the development and application of methods and algorithms for the simulation of soft matter systems, with a broad interest in statistical mechanics, in particular non-equilibrium statistical mechanics and recently active matter. Now, the reason why Ignacio is speaking today is because CICAM coordinates within its network one of the active centers of excellence for computing applications funded by the Horizon 2020 program. Our center is called ICAM, and I think that Ignacio is going to describe it and its scientific outreach for us. Thank you, Ignacio.
Thank you, Sarah, for this introduction. Let me see if I can share the screen. Can you see it?
Yes, we can.
Perfect. Thank you. So, yeah, as Sarah says, I am here acting as the coordinator of ICAM, and I will go with you through what it is initially, and briefly, and then I will try to focus on a few examples on how this type of initiative has helped us to catalyze activities in the development of software in the context of the new and the developing H.P.C landscape and the science that can be done with it. So ICAM is a center of excellence. Center of excellence are projects funded by the European Union, and they basically aim at addressing the challenge of developing software and codes and algorithms to exploit the developing landscape of hardware and coming new machines for high-scale, high-performance computing. And basically, ICAM builds on CICAM, on the network structure that CICAM has developed during this century, let's say. And basically, it's composed by 16 CICAM nodes, but also includes 4 praise centers that are associated to these supercomputing centers, in particular iCheck in Ireland, IDRIS in France, the center Jülich, the supercomputing center, and then also CSC in Finland. And there is also a center for industrial computing, Hartree Center. And also we have engaged 12 industrial partners in the activities of this COE. As I said, the objective is really to address the challenges in a broad sense that H.P.C is bringing. And in ICAM, in this broad context, has as an overall objective to create, develop, and sustain a European infrastructure for computational science that is applied to simulation and modeling of materials for modeling of materials and biological processes, so quite broad. And also, it has the interest or the specificity of trying to establish close links with industrialists so that then we can, on the one hand, facilitate the transfer of knowledge and also to make them easier for them to understand and benefit on this new possibilities that H.P.C offers to them. So in this context, this project has three main goals, or three legs in which we have been developing. One is on the development of software, and in particular, what we call software modules, which is a way of emphasizing that this development tries to be transverse and open to the community, with the idea that then this development that we produce, it can be used in academia and industry. Then it also has an important aspect associated to training. It's important to train scientists and the professionals that are needed to the development of methods and software towards this high end of H.P.C. And then also to support industrial end users, as I mentioned earlier, and then also try to bring them and to understand how they can benefit from these new possibilities, and also catalyze closer collaboration between academia and industry. As I said, we cover, ECAM brings quite a broad range of expertise, and we are developing activities in software and scientific software in different areas of material science and biology, as I mentioned earlier. And basically we structure that in 4 work packages, one about efforts in classical molecular dynamics, another one on electronic structure. There is also activities on quantum dynamics, and a 4th one about meso and multi-scale modeling. In terms of the parts that is associated to software development, which is what I will be focusing in the rest of my presentation, if you want, the goals of the efforts that we carry out is that should be user-driven. As I said, it has to be also focused to exploit H.P.C resources, and also to develop H.P.C or to transfer H.P.C best practices into industry, or more generically into a new type of users. The development of software modules that we carry out has a broad range of applications, and we do that on the one hand by employing researchers that engage into projects which have a connection to an industrialist, either a big company or an SME, so that then we can identify computational efforts and software development that will be of interest in that respect. And also, whatever we produce, we make it sure that it's open access. So we have a software repository. Actually, you can visit it if you want, where we we list what is the software that we have produced, what modules. Module is a very general term for software, a piece of software that can work, or that has been shown that it works well and it can scale for an H.P.C environment, that can interfere with different type of software that is used by the community. And also, beyond that, we have identified specific need and develop interfaces that combine software models with the standard codes and that can run on exascale computers, and then also combine them with devoted software activities that are more transverse, that address the specific bottlenecks that we have identified through this practice in ECAM that are of general interest. And that's the first part that I will focus a bit more in detail. Basically, one is about high throughput computing. Cecilia already talked about the relevance of high throughput computing. Then also code refactoring into libraries of big code. So for example, in the case of electronic structure, we have made the effort to develop a set of libraries that can interface with many of the different type of codes. And also we have focused on the importance of load balancing for the subset of codes that are particle based. So in particular, so as I was mentioning, we have identified a number of bottlenecks that are particularly relevant when moving towards the exascale, and that in a way go beyond specific modules or specific codes that I was referring to earlier. And we have also then devoted an effort to develop libraries that can be useful for all these different or fraction or a good number of these different activities that we are carrying out, and therefore we also think they are relevant in a broader sense for the community. One is about load balancing, and there exist already solutions for load balancing, but then here the effort is to create, as we scale up, the dynamic load balancing becomes a key requirement. And then it was important, we thought it was relevant to develop a generic library that can be implemented in a variety of algorithms. And actually we have already been doing that with a code that is part of the initial partnership with ICAM, which is a DPD implementation by the team in the Hartree Center in the UK. It's DL MISO. And also we have been in collaboration with members from another COE called Biomed. Actually, Peter is here. He's the coordinator of this Center of Excellence, actually also in exploring how this library is useful for an implementation of a lattice-Boltzmann code for blood flow, and I will also come back to this. And the other transversal effort that we have made is how to think about developing also a high throughput computing framework that is flexible enough, that is can schedule multiple tasks, that is MP aware, resilient, adaptive, and that can be also quite well adapted for the challenges that come with the exascale machines in the near future. And then again, here we have built on specific projects and work on a real events project that we carry out from the beginning of ICAM as a proof of concept of this type of new HTC environment. And just to conclude, I mean, we have also been exploring COCOS as a way to have a promising enabling closed platform performance portability, because one of the challenges of these new H.P.C environments is the fact that one has typically to run or to address the fact that codes should be able to work on different and heterogeneous architectures, and that's also a specific challenge that needs to be addressed. So what I want now is to show you what we have done in these two aspects, and then I will move on and then go back a bit more in detail into the effort done in one of the projects in terms of how to reshuffle or recode the code to be adapted to these new environments, and in which sense this is scientifically engaging and which type of possibilities it opens, makes possible. So, as I said, one of the transversal software efforts that we are carrying out is the development of this load balancing library. It's called ALL, a load balancing library, not very original name. And this, what is specific about this library, I mean, the generic challenge of load balancing, I illustrated here on the right with a very simple example. This is a collapsing polymer gel simulation where, because of its collapsing, then a lot of particles tend to accumulate in one particular part of the whole system. And basically the goal of load balancing is to redistribute, when you run in parallel, the size of your, how you partition your system to have a finer partition where you have a larger effort. And that's quite generic. This is an example with a staggered mesh load balancing. As I said, when scaling up into large H.P.C environments, then it's important to have a dynamic balancing in many cases. So this library actually has either the possibility to have static or dynamic, and then again, whether you go one way or another, you have to face which are the advantages and the costs. And also, it has been enhancing its functionalities to include tensor, product decomposition, staggered mesh, Voronoi tessellation of topological meshes to be able to adapt to a larger, wider variety of codes and needs in this context. So this is a library that's connected to user communities. Again, we all the efforts that we carry out in ICAM, again, don't want to reinvent anything. I don't want to have a kind of a small or closed piece of software, but rather possibility to be as transversal and as versatile as possible. And we benefit, I mentioned at the beginning that one of the legs of the ECAM, we also carry out activities and meetings to train new people, and we actually has also led to what we call extended software development workshops, which is a new type of activity for us where we bring together to work and development on and analyze scientific challenges associated to software development and bring people to work on them. And for example, we have had meeting to bring people from different communities or working with different codes, particle-based codes, to discuss what are the needs they have with respect to load balancing, also as a way to adapt or develop, to co-develop, if you want, the library that can be more useful. And that has led to ongoing works to adjust them to develop, to ensure that this library is as versatile as possible. And just as a simple example to give you of a particular activity, as I mentioned, we engaged with scientists in this other COE called Biomed, associated to Peter, where they had a lattice Boltzmann code for very large and scalable applications. And the goal of this code is to study blood flow in realistic vasculature geometries. And this is quite, as you can imagine, there are serious issues with load balancing. They had their own implementation, and then actually we could compare their implementation with the performance of this library. And it's also an interesting example because, I mean, here you have examples of this vasculature, the geometry, and then therefore the need to have an appropriate redistribution of how to partition the system. And actually that led to identify that there was an issue with also how generically the Intel works with this type of code. So that also led, after this initial interaction, to an interaction with POP. We heard about POP, which is a COE specialized in analyzing performance in these H.P.C environments. And because, I mean, both the original implementation for load balancing and all work well up to a certain limit. As you increase the number of CPUs, at some point, the scalability is no longer there. And there is a question of where is about the details of how you do this load balancing become relevant. And therefore, having two different ways to do that was a good way to really signal out that there was an issue also in how the code interacts with the underlying architecture of the computer. And that can lead to further discussions and a co-design for these large H.P.C architectures, which I think it's a good example of how subtle this may become and how important it is to have these devoted libraries that allow you to try to identify how to best, on the one hand, balance, and then where other bottlenecks may appear, which sometimes are unexpected when sort of scaling towards this excess scale. Now, the other, as I mentioned, this is a brief for H.P.C. We have developed this library, and that interfaces quite well, in particular with the work that has been done within ECAM in a particular implementation of a transition path sampling, which is called open path sampling. And that has actually allowed to carry out simulations on doing substantial averaging or statistics on rather complex biomolecules. And that put us as an example, I mean, when, again, related to the current crisis of COVID, the Commission sent a specific program for projects to analyze or to work on issues associated to the understanding of COVID. And having developed this H.P.C and having developed the open path sampling within ECAM, position ourselves in a position to take advantage of this opportunity. And actually, this is also an ongoing activity to study for example, the two stable states of a particular set of residues of one of these, the main proteases of the SARS-CoV-2. And again, that's an example of how developing the corresponding tools that allow one to really address these complex systems provides you the possibility to do science when needed. In this case, quite short notice that otherwise it would be quite demanding. I would say, and this was also emphasized by Cecilia, taking advantage or really exploiting these coming exascale machines is not only a question of being able to run very large systems for long times, but also is the possibility to have to exploit these environments to increase substantially the possibilities to do statistics or to sample complex or high-dimensional parameter space. And that in itself, or also for material simulations, can become a game changer in the terms of how you can identify phase diagram or how you can identify the properties of materials over a large variety or large set of control parameters. So these are, I would say, two examples of how we have developed this type of software that I think is really functional for this high-end H.P.C. and which can be useful for a number of codes. In the rest of my presentation, I wanted now to move to a particular set of activities that have been done in this case around, I mentioned about the different areas. One was about meso and multiscaling. In the area of mesoscale dynamics, we have been carrying out also efforts to adapt and to develop software that can benefit from this H.P.C. with a scientific goal. And basically, this is about a particular type of mesoscale modeling that is called dissipative particle dynamics. Actually, it was introduced in the early 90s by Jorge Brugge. And so in a way, it's a relatively well-established method. The advantage of DPD, or the peculiarity of DPD, is that particles are point particles, and they can be seen as an effective particle. So it can, for example, if you think in molecules, it can represent a set of atoms or a subset of a molecule. So one loses a chemical resolution, or one loses the atomic structure of the detailed structure of the solvent. By doing that, then the effective interactions, if you think in an effective force between these ensembles of atoms, then is softer, and you have less degrees of freedom. So both approximations allow you to reach larger time scales and also to simulate system over larger length scales. And therefore, it is interesting and an interesting approach to model materials on larger scales that you could do otherwise with molecular dynamics. What is specific about this DPD approach? So in that sense, if you would think in these usual diagrams in terms of length scales, I mean, you can have a much more detailed, realistic simulation at the atomic level with MD, and then you have this regime, intermediate regime, before you go into more continuum dynamics approaches, this mesoscale area, and that's where this DPD would sit. What is specific about this DPD then is that actually the dynamics is very, formally, it's like the dynamic equations you would write based on Newton's dynamics, but the difference is that the force acting on each particle has a conservative part that would derive from an effective Hamiltonian, because we are talking about these effective forces. But then there is a thermostatic, so there is a dissipative and a random part. And what is specific of this is that these forces act also on pairs of particles. So it's a friction, for example, that depends on the relative velocity. And as a result, that conserves momentum. So this ensures that when we go to larger scales, for example, in the case of a fluid, the Navier-Stokes hydrodynamics will emerge out of this dynamic. So this is a method that allows you to capture consistently the dynamics of the system, and therefore it can be used not only to study the equilibrium properties, but the process, for example, of a material. And in that sense, it's attractive for the simulation of complex materials. I will be talking about DPD is the method. There is a code DLMISA referred to. This is developed by the Hartree Center, and that's the one in which we have been within ECAM working on software development. And again, this is used for example, if you think in a bilayer or in a vesicle, then here you really need to compromise in the level of atomic detail to be able to have a relatively large, say, membrane, or for example, to be able to simulate vesicles, then otherwise it would become too expensive. The goal of developing this DL-MISO, or in general, the possibilities that DPD open, go beyond and open the possibility to really think in having a computing aid formulation as an alternative way to study and to analyze or to explore new materials. And that is really a radical shift in process for formulated product design that goes beyond the usual ad hoc intensive process that goes experimentally. And basically the nice thing in that case of exploiting mesoscale modeling is that one can, I will be talking about surfactants because that's a particular type of systems that the team in the Hartree Center has been focusing a lot, and then that allows to increase the achievable system size and timescales, as I said, to reach scales that are relevant industrially. And then for that, one has to use a highly scalable DPD code, and actually some of the efforts done has been to adapt or to rewrite the code to run and to exploit GPUs. And as a result, the idea then is to have an integrated data analytics and modeling simulation platforms. Actually, the idea by the Hartree team is to provide an integrated then product where the user can have an interface, and behind that, obviously, you need to access supercomputing facilities, but then you can integrate high throughput chemistry so that then by exploiting these processes, then one can identify force field development, one can prove or examine systems or materials under quite generic conditions. And also they want to link that, they can produce data, and then you can also exploit the data as well through data analytics or doing machine learning as well. So the fact that the possibility to have this very powerful machine, then it's like the basis to then build a whole environment that then can be used to start formulating or exploring materials in a qualitatively different way. Now, that in itself is quite challenging. So focusing on how to do this simulation or providing this modeling environment that is consistent is quite demanding. So it requires parametrization. And again, there is a lot of effort done in how you can use, for example, partition coefficients to try to calibrate the parameters of this DPD, which are to some extent effective because these are not atomic potentials that you're with to try to quantify them. And for example, if we talk about surfactants, because they form micelles and mesostructures, then sometimes it's not only thermodynamic properties, one needs to ensure that the relevant structural or morphological properties are recovered. In that sense, for example, they use CMC as a way to identify when micelles start appearing and make that computationally, calibrate so that it's quantitative with respect to experimental conditions. And that in itself is quite demanding. For example, to extract this partition coefficient, one has to go to a few million bit simulation. So for example, to look at this CMC, one needs to be able to simulate systems that can produce a few micelles, which also require large system sizes. So that's computational cost is not for the sake of it, is because to be able to achieve this possibility to have this calibration. And once you have that, you want a whole phase diagram. And then here, for example, you can build, in the case of the surfactant, in rather than having, one could do this H.P.C we're referring to. Also, a possibility is to start with simulations or experiments. That's actually comes from experiments where you put pure water with surfactant, and as the two water and surfactant start mixing past to each other, because locally the concentration is different, you can use doing the slices, you can guess what are the different concentration and the corresponding structures. And this is quite an ingenious way to, again, through a simulation, try to go from the high concentration to a low concentration surfactants and then predict phase diagram. And it's more laborious, but they exploit the same idea for ternary systems, in that case with surfactant, water, and oil. And again, that, for example, led them to identify a complete phase diagram, which is something quite involved. But that's needed to be able to have possibility to do realistic simulations with these mesoscale systems and to become useful from this formulation point of view I was referring to. And they have been exploiting this, for example, to study a particular set of surfactants, alkyl sulfates, and they have identified the type of morphologies that appear, and for example, also how changing the salt, they change the structure and how that affects the rheology. So it becomes a real tool that you can exploit. I wanted to mention that, as I said, this is quite intensive. So to be able to have this plan that allows to go from a model calibration and then prediction and exploration of new materials, one needs really powerful underlying machinery. And one of the recent things that have been done in the context of ECAM has been to port this DL-meso to GPU. And again, if you want this approach, as I told you, DPD is quite similar to what you would formulate for molecular dynamics. So you can have a host CPU and then pass to the GPU, as you would do for any of these particle-based simulations, the construction of neighbor list and then identification of forces and computation. So in that sense, the basic structure it's clear. When it comes again, how to exploit it so that it can also be an efficient way to have a GPU implementation for multi-GPUs, then they had to address the challenge associated to the memory access, because if you base, as sometimes you do in GPUs, the structure to particles, then the particles that are interacting within a cell do not need to be consecutive particles in memory, and that has a cost. So they sort of like re-express everything in terms of cells to maximize to optimize the access to the memory. And actually for one GPUs, again, it shows quite very good scaling as you increase the number of particles, the speed up that you get on the GPUs. And this is for both, I mean, it's a bit more technical, but you can introduce, in the case of charges, also smear charges that have long range forces, and they test the speed up both for short range or long range forces, and the speed up is general. And then the challenge really was to go to a multi-GPU environment. And then here, this is the scaling as a function now of the GPUs. And you can see that the scaling is, I mean, this is the ideal scaling. So it's quite good, up to 4,000, more than 4,000 GPUs. And that's systems with 1.8 billion particles, which shows you the systems that you can reach and the power of this method and how it works. So they have been now making tests on how this scaling works, for example, for phase separation of a binary mixture. And actually, you can see here different times how it works. And actually, they recover. This is a non-trivial result what you see in 2D. In 2 dimensions, you have like this intriguing structure where you have like droplets inside droplets inside droplets, which is characteristic of the kinetics of the phase separation. And in order, I wanted to finish by pointing out that then one can exploit, and I think that's a generic statement, the power of computing by having an appropriate code, but also having an appropriate algorithm. And actually, when looking about phase separation, this was a two-phase system where we have equal density. So you need to do, I mean, it's like oil and water. But actually, it's possible, I mean, for this DPD, it is possible to develop an effective force that allows to lead to a coexistence between a water or liquid and a gas. The standard DPD forces are short, I mean, they are soft, and they cannot sustain a condensation transition. But it's possible to generalize the type of interactions by saying that the excess energy between two particles depends not only on the position of the particles, but on the relative density around each particle. So this is, if I have particle I for around all particles around particle J with a certain weight function, this is a weighted density. And if you consider an energy that is nonlinear on this weighted density, then you can have a coexistence between a liquid and a gas. And that's relevant not only because it's a proper condensation transition, but also it also means that the computational effort, I mean, if you see, I mean, this is for this particular choice of, these are the forces that derive from this energy. So it's quadratic in the energy, so it's linear in here, the force is linear in the energy. You can have a coexistence with a gas that it's almost at zero density, which then it means that by thinking about this ingenious type of interactions, effective interactions, because again, we have this mesoscale method, the computational effort is really focused where you want, which is in the liquid. You basically do not have to do much to keep track of the liquid to the gas. Again, because this is a force that involves this weighted density, there was the need from a point of view of this porting to GPUs to readjust the porting to account for this particular type of forces, but that's something that, again, they did. And then in this case, if we are thinking in this liquid gas coexistence, then obviously most of the effort is made where the liquid is, not where the gas. So again, they introduce or they use this load balancing library I was referring to into DL meso to be able also to benefit or to maximize ensure that what they can sort of benefit from this scaling if you have now a liquid gas system and a large system size. So this is to finish a simulation to test how it works. So now we are not talking about a billion particles. This is for few 100,000 particles only, but just to show. And then this is for not for a liquid-liquid phase separation, but this is for liquid gas. So here you will. This is the total system. Here is how the system is partitioned, and this is a cut across it. So you will see it as a function of time. And here you can check the load balance between the different GPUs. So this is run on 8 GPUs, sorry, as a function of time. So as you can see, the phase separation will create drops. These drops then, as they coalesce, they will become larger, and all this black space essentially is the gas where there are no particles. So that's what I told you about this algorithm, that really there is no computational effort here, and then accordingly also the partitioning of the system accommodates dynamically to basically spend the time where particles are, and this is an example of how the load balance between the different GPUs is really kept in balance between them. So I think this is a good example. We now can think of running this with a billion particles and how you can really combine the choice of the method, a proper algorithm, and then a proper parallelization. So I'll finish here. So I think I've shown you how this project has helped to catalyze all these activities about software development and both handling or facing the development of tools that are useful to benefit from this high H.P.C end, and how also we identify the specific. I mean, we have done other efforts. I mean, on the ECAM webpage, you can see the different scientific projects that we are still developing. But this is an example about how you can use this. We have really adapt this DPD, this DL meso, to be able to be a really powerful machine for formulation and material modeling. And thank you for your attention.
And thank you, Ignacio, for this presentation. I must say I was a little jealous watching this last example, because I live at the opposite end of ECAM, and I deal with quantum dynamics, and we're usually very, very happy when we are able to find approximate solutions for the time-dependent Schrödinger equation for 50, 100 degrees of freedom. So I think this is a nice illustration really of the multiplicity of scales that we try to address within this project. So let me invite again our viewers. If you have questions, please do not hesitate to ask them. You can use the chat, or you can send an email to director@cicam.org. Now it is my pleasure to introduce the last speaker for today's webinar. This is Professor Peter Coveney. Now, Peter is a scientist with an impressively broad range of interests, ranging from condensed matter physics and chemistry to materials, to life and sciences and medicine, which is, I think, one of his signature interests. These vast array of different scientific problems are united by the fact that they all require advanced use of supercomputing capacities in order to be tackled effectively. And I think that this is particularly relevant and explains in part the engagement of Peter as a leader of the ConBioMap project that was mentioned by Ignacio, where he focuses, I think, mostly on an area of which he is one of the pioneers, which is that of computational biomedicine. And this is what he's going to discuss in his presentation today, in which he will share with us his views on the transformation of medicine that is made possible by the use of supercomputing facilities, with specific focus on the COVID situation. Peter, thank you very much for joining us today.
Sarah and Ignacio, I hope you can hear me clearly. I want to thank you both and everyone at CCAM for kindly inviting me to contribute to this fascinating afternoon. And it's nice to be able to say that we kind of know each other and have collaborated in some respects. Ignacio was talking about some things we've done as a result of these centers of excellence interacting with each other. And Cecilia was talking about MolC, which I have a fair amount to do with as well. My talk, if I can manage to get it projected for you all. Let's see if that's visible. Could you let me know if that's kind of full screen now and visible?
Perfect. Full screen now.
The title of this talk, because of the request to give a fair number of presentations in the area of COVID at the moment, since that's become a pressing source of concern to all of us. And if you're working in computational biomedicine, it's something, it's almost an imperative to work on and an opportunity. I want to convey that to you. The title of this talk is largely taken from an invitation to speak at the International Supercomputing Conference, I think a week or so ago, where a kind of unusual plenary session was set up immediately after the top 500 was announced about the relationship between high performance computing and COVID-19, essentially. And there were talks by 3 people at that. And I want to talk around that topic. I want to expand it a bit to make it slightly more, as it were, scientific than technically dominated as that presentation would have been. And I want to give you an idea of the sort of things we do, the nature of the sort of challenge that's facing us collectively in the wake of the pandemic's eruption, how supercomputing is playing and must continue to play a central role in this. And indeed, what difference it can make if you're able to strike up collaborations at a scale at which, you know, what you do can make a difference. So I'll just give some examples of our research in action there. But there are several messages here, of course, about the nature of science in the medical domain and the way in which modeling and simulation is surely set to make a big difference to it in the future. So I think we're all aware of the general predicament we're in. Just in statistical terms, the clock continues to tick. There are more than 500,000 deaths now and 10 million confirmed cases. It's impacting most of the sort of countries in the world. But the issues, if you're trying to address it, are fairly self-evident and need to be articulated and addressed directly. I mean, the fact of the matter is that if you're relying on the pharmaceutical industry to come to the rescue, just remember the statistics that on average it takes 10 years and of order $3 billion to produce a single drug. That drug is meant to be a blockbuster because the whole model is supposed to be one size fits all. You invest so much money, you make one molecule, it had better work for everyone, hadn't it? Well, wait a minute, don't we live in the post-genomic era? I thought we believed that genomic sequences and other things had a role to play in this. And of course they do, because it's also a fact that barely a single drug that is ever brought into the market will work for more than 50% of the population, although that's not often appreciated. And of course, in certain cases, far, far less than 50%. So it's a general problem anyway. And in this case, needless to say, the treatments are supposed to be delivered at pandemic speed. This just erupted on us, largely in Europe, at least in the phase from February to March. And then suddenly we're engulfed by it. How are we going to resolve this situation? So just also to remember that the pharmaceutical sector's model is broken in its own terms, in that financially 2020 is the first year in which it becomes unprofitable at all to make drugs. This profitability margin has been decreasing linearly for the last 10 to 15 years. So in a sense, we're in a bad situation. The question is whether we can do anything to reverse the predicament that we're in. And I'm just going to try and talk you through what is possible, what I find, in spite of the predicament we're in, kind of interesting and actually scientifically, at least, highly motivating. And really, that's where the role of kind of advanced information technology must be brought to bear. And the reason why drugs take 10 years to develop is to do with 2 or 3 sorts of things. But in the early stages of drug discovery, it's an extremely laborious laboratory-based procedure of making compounds. Of course, many pharma companies don't really make them anymore. They farm them out to other people to assess, or they go around trying to buy biotechs that think they've got a drug that they'll be interested in. And then there's all this time delay during the clinical trials periods, where things often go wrong and famously fail late, and at late stages in that process of 10 years can be extremely expensive. So I put it to you that if we're going to do better, we have to invert the model, because the role of modeling and theory in pharmaceutical sector at this point in time isn't very impressive. It's like what happens in most of the life sciences. Life science and medicine's on the extreme of this mapping out from the areas that CCAM comes from and knows and loves. Let's say the physics and chemistry communities, we've got applied mathematics and engineering in there. So if you talk about those areas and you ask yourself, what about doing science and publishing papers that use theory, modeling and simulation? We all know you can make a career out of it. And it means you can write papers and they can make a big impact on their own. But if you go across the spectrum from the hard sciences, if we call them those, to the softer ones, personally, I think I can point out a position in this spectrum of journals at which it no longer becomes possible to submit papers to that area which are led by theory or modeling. I think many people will recognize what I'm getting at. It means that if you're going to contribute modeling and simulation in the biological sector, you need to add it on after the event. It's what we call post hoc sort of rationalization of what's observed in the laboratory. And as you go further across to medicine, this trend becomes even stronger, that empiricism dominates everything. And the idea that you can actually rely on a computer to predict something is almost anathema and a shock to people. It's important to understand this, because as someone who operates in that, and with a center of excellence whose job is not only to do sort of leading research, but to engage with the community and expand it, we do have education and training challenges here. Because it's clear, I think, from what I'm getting at, that what we need to be doing is putting modeling, simulation, theory in front of experiment. Because we have to, if you're going to do personalized medicine, you have to be able to make predictions, and those predictions have to be credible, and they've got to be actionable in the sense that people discuss them in other areas, particularly, let's say, engineering science. That's obvious. One could criticize the physics and chemistry community a little bit for the idea of how reliable their predictions are if it comes to the crunch of an actionable decision, such as, are we going to put someone's life on the line by following the outcome of a simulation? Clearly, if you do engineering and you build structures which people are going to live in or depend on, you have to handle that. And equally, if you're going to use computing, modeling and simulation in the bio sector, particularly medicine, which is the thing I'm most interested in at the moment, then I want to have predictions that are credible. Actionable predictions mean people will believe what I tell them and carry out some form of intervention or clinical decision that's supported by it. So that's really an interesting challenge. And it's, I would think, kind of at the apotheosis of what we're interested in computational science. We have very complex systems. The biological ones are extremely complicated. We need to get data, typically on individuals. So we have information governance problems to bring the models and the data together. And then we need to get the results in a hurry, meaning fast enough to influence a clinical decision. And clinical decisions may need to be taken in half an hour or an hour or a few days. So getting all of that to work is quite a challenge. And in an area where many of the people who work don't quite understand what we're talking about, it's even more tricky to do it. But I just remind you, the analog is with weather forecasting, which is now quite good over short periods of time. We use supercomputers and we try to solve quite complicated systems of equations, and we make predictions about what's going to happen tomorrow. And generally, people listen, and the actionable decision, especially if you live in London, where I do, the weather can change a lot. You not want to know what the weather's going to be like. Maybe you need an umbrella. That's your low-level actionable decision. But in these other areas, particularly medicine, the stakes are much larger. So what I'm saying in this slide is really about actionable decisions. First, we need to make sure that our modeling and simulation is certified in some way. And that includes what I call an acronym of VVUQ. You can see the lengthy words down there: verification, validation, and uncertainty quantification. So that's what we have to do anyway to make our predictions reliable. Typically, the outcomes are never deterministic. It's a probabilistic outcome that we're looking for. And if we're going to do that in biosciences, let alone medicine, the paradigm shift is that we have to actually understand how to build models and do simulations in a way that means they're reliable when the predictions are made. So it's quite a tall order. This is just an example of something we were doing some years ago on HIV, but it's kind of transferable to what's going on with any viral infection, modulo a few issues. For one thing, HIV infection or viral infections are really multi-scale, and depending on your expertise or interest, you could end up anywhere in that picture, from worrying down at the bottom sort of left-hand side about how the life cycle of the virus is conducted once it invades the host cell, and how I'm going to design inhibitors to stop it, through to higher levels, which involve ultimately actually the infection and immunity, the immunological response. That's where we're interested in vaccines. But at upper levels, it's the network dynamics of the epidemic at a whole human and population level. And of course, many of those things matter in a serious way. And although I won't be talking much about this at all today, one of the things we got interested in the UK recently, let me just preface this by saying the UK did not distinguish itself by how it decided to deal with the pandemic once it came down on us. We had quite a lax approach to it, but then suddenly an advisory group to the government became famous in the UK popular press because they were using modeling, actually like modeling and simulation, to advise the government as to whether they should conduct a lockdown or not. And the lockdown decision that came in the UK in the middle of March was, a few weeks after Boris Johnson had felt that that the British had a so-called inalienable right to visit the pub, and he didn't like the idea that people would have to be locked down. The epidemiological models that were put to him showed that if he didn't take action, in the UK, there could be over 500,000 deaths. And it sort of focused his mind, and lots of things happened. So these are models that are real world cases that influence outcomes for all of us. Can we believe the decisions that government and politicians are taking on the basis of models? So I have a project currently at the moment looking at how reliable such epidemiological models are. I'm not going to discuss that any further now. If you're interested, before long, we may be reporting our findings of that. But so the point is that this is an infectious disease, just like the case of coronavirus. And there are some things that are transferable from the way we model these things. They're fascinating systems from a conceptual and theoretical point of view. I mean, the generic thing is a virus. Some people might think it's kind of a fossil from the origins of life, if you believe the RNA world view. These RNA molecules are there in a Richard Dawkins sense of being able to replicate themselves. That's how they survive. And they're very robust and resilient. But you know, you have something like an RNA strand at the heart of these things, and then they insert themselves into a host cell. Once they're inside it, typically in the case of HIV, for example, the RNA is transcribed into the DNA of the host cell, and then it just generates lots of proteins that relate to the virus. That virus then it develops itself into a new virion particle, aggregating all these individual proteins. So the protein that's actually being produced initially is a very large thing. It's a polyprotein chain. And the key thing in COVID-19, just like in HIV, is or are proteases, because the protease has the job, as it were, first folding itself inside this polyprotein chain, cutting itself out and going along the chain and cutting out all the other pieces. So it's obviously a good target to try and stop. And that's why people are looking at the protease analogs in COVID-19 to stop the protease from helping to build a new mature virion particle. This is just a small picture to show, yeah, we do some mathematics in biology and medicine, but we don't usually show them even when we try to write theoretical papers in the subject. This is just showing the nature of the kinetics. There's quite a nice sort of mathematical structure about the way in which the polyprotein chain gets cleaved. It can be represented in quite a condensed way. One of the issues is you get a lot of parameters cropping up. These Ks you can see in the boxes, these are rate coefficients for all the individual rate processes. And that's one of the sort of challenges if we're doing modeling here, to know what the parameters are or to be able to infer them from experimental measurements. And if you're dealing with the immune response, having gone quite quickly through the description of the process by which the virus sort of converts itself into these proteins inside the cell, then the issue becomes the one of how does the immune system inside the cell find out or figure out that it's been invaded. And this picture is related to some work we were doing a few years ago. Much of the structure, as anyone who likes theory would attest to, is that you've got a theoretical structure for one system like this, then it's quite transferable, not in whole, but in some broad terms, to the next one, which is COVID-19. So the message that should come through from this is that if I understand some theoretical principles here, I can build a model for COVID-19, which is quite interesting and tells us a lot about where we can design inhibitors and where we can do vaccine predictions. So in this case, I'm just trying to take you through a few examples of what happens. They've got these proteins which are foreign inside the host cell. The host has to do something to get rid of them. It's always chopping up its own proteins as well. So it's got to distinguish in immunological terms, self from non-self. When these fragments are broken down by the proteasome, the sequences of amino acids that are in them are the key to knowing whether the fragments are from the self or from the invading pathogen. And then there's a series of steps whereby the fragment peptides get onto the endoplasmic reticulum and attach to MHC, which is the major histocompatibility complex. And at the end, they find themselves on the surface of the cell in unique sequences of amino acids and with a time dependence that's specific to their nature as well. So in principle, you have a model here that will tell you the time evolution depending on the genomic sequence of the invading pathogen and the time ordering of the processes internal to the cell when they will appear. And this is related to the so-called statement of immunodominance, which are the dominant epitopes that emerge on the surface and their time evolution. So, we published a paper on this 2 years or so ago. From what I said, you wouldn't be too surprised if I say it's not the easiest thing to then get a paper like this into a biological journal because there's no experimental evidence at this moment. This paper is making predictions. And as it happens, the experimentalists still today can't resolve the time evolution and the appearance of these individual sequences. So this is just an example of where the theory can get ahead of experiment, and I suggest ought to be there and challenge the experimentalists to verify or otherwise. So that's a picture. I won't dwell on that, but it makes time predictions, time course of the appearance of the individual epitopes. I'm going to go back now to the more conventional area that we know and love in CCAM type areas, which is the biological thing for drug discovery, and just quickly whip through this. We know the problem, I spoke about it at the beginning. How long does it take to discover a drug? And it's the needle in the proverbial haystack. How do I find the thing that's going to bind as a small molecule to a protein? So the question there is, how do you do this stuff? And I'm suggesting that the pharma sector hasn't really been doing that very well. We need to find other ways, faster ways, putting modeling and simulation in front. Here's what's happened for us in the context of COVID-19. I'm involved in the Center of Excellence, which is this EU one in Biomed. It happens to have in its partnership 2 international players, one of whose faces I saw in Cecilia's description of MOLSI, and that's Shantanu Jha, who's at Rutgers and also now Brookhaven. The other one is Rick Stevens, and he runs, he's a deputy lab director at Argonne National Lab. He's also a kind of computational biologist there. So with him, for the last few years, we've been working a bit on cancer modeling and simulation. It's a combination of machine learning and more conventional physics-based methods. This is the grouping of people that has been able to sprout from almost nowhere instantly during the last 2 weeks or so of March. So there's a large number of US DOE labs involved, coordinated by Rick Stevens. Comp Biomed is in there, 1 or 2 other entities that we'll recognize. And I do want to emphasize this is an open collaboration, by the way, and other people are welcome to participate. I've put Leibniz Rechenzentrum in there, which is probably known to many here. It's the lab in Garching near Munich. We use some of their resources in a major way. But the consortium is emphatically not just doing computation, because I'm never for a minute going to advocate we do theory and modeling in this space without experiment. That would be utter waste of time. The issue is really, can you get enough of a critical mass so that if you do what I aspire to, which is model and simulate in various ways, you've got people on hand who are experimentalists who work with you to assess what you've got. So this environment has a lot of experimentalists. So unlike maybe a more conventional pharma development, these experimentalists are aligned to listen to the predictions and output from the modeling and simulation. And then we have people who do assay developments that will be able to test some of the predictions that are coming from the models. There's structural work from being done with these synchrotron sources, and indeed chemical synthesis work. So what I find interesting about this is turning the conventional model on its head and seeing if we've got any chance of making interesting discoveries. I throw this one at you because I mentioned to you VVUQ earlier. Another project that I currently lead, it's a European one, and its URL is written down there, is on the development of software for VVUQ purposes. It's an open source project. We've had 2 years of annual releases so far, and it's also open development. It's particularly interesting and applicable to multi-scale applications, which is an area where uncertainty quantification is really totally underrepresented in any domain, to be honest, at this moment in time. So quickly moving from there, the picture of joining machine learning and MD, I don't think this community needs me to talk through this. I can be sometimes quite critical of blind big data methods because they are full of pitfalls. But I think in this community, people know why they're trying to use machine learning and keep it in a straight and narrow path, which is trying to support theoretically based research. So it's all about doing some parts of the search using machine learning methods to find opportunities in the chemical space, putting them together with methodologies, typically free energy predictions from molecular dynamics, and then doing iterations to improve the research predictions. So we're able to now look at very large libraries. Some of them are physical libraries that you can sort of assess through modeling and simulation, just docking in the first instance. And then of course, there are the generative methods that can try to probe a chemical space that hasn't been synthesized. In a problem like this, it's self-evident we tend to be looking initially for repositioning of existing drugs so that they can get out early. And so that's the focus on the first wave. And these combined methods are, at this point, actually able to produce quite a lot of compounds that are being evaluated within that consortium. So it's quite nice to see one's ideas rapidly coming into an experimental setting. The drug development things we do, and I don't want to dwell on them, you are interested in hit to lead. This is the conventional idea of a large, diverse set of compounds after the machine learning has been deployed, trying to get good rankings of the best molecules to take forward. And then there are things, fashionable approaches like free energy perturbation at this moment and thermodynamic integration we use. Whenever we do these things, we're very careful about the uncertainty quantification. So that goes back, I think, to something Ignacio was saying earlier, the importance of being able to run lots of replicas. In fact, that underpins most of uncertainty quantification is key here. And to be able to do that, you do have to have powerful computers with many nodes on them. This is just a nod in the direction of the computers we use in the collaboration. And you'll see 2 or 3 sizable computers there, which were at the positions declared when I wrote this slide, but have slid down by 3 or 4 places since Monday, whatever it was, the 23rd or something of June. But they're very powerful, and they have typically combinations in several instances of hybrid architectures where you can run multi-core and GPU or combinations of them. In the US, we have access to similar types of machines. And then we have middleware that is important to us because it enables us to run so-called pilot jobs, which means massive campaigns of calculations that take up large parts of a computer and then deploy workflows on them. So the workflow structures here have stages that I haven't got time to go in detail, but link all the phases together across these machines. It doesn't have to be only on one, and that then can produce results in quite a hurry. These are examples of the performance metrics and how well they make use of the machine in its entirety. And one of the things I thought might be of interest here, after Ignacio was extolling the merits of converting your code to GPU and so on, some codes might run very well on CPUs and others on GPUs. And there is an embarrassing issue that's known to resource providers, but never seems to be discussed by other people. And that is that when you deploy a GPU intensive application on a GPU type machine like Summit, you typically don't make use of most of the cores. And equally, you could deploy a CPU intensive code on that machine and you wouldn't be using the GPUs. All kinds of things like that do happen. But if you have this type of middleware that I mentioned, the radical one, it enables you to interleave the applications in a rather nifty way. So it happens that we have codes that do this thing called ties that only use the multi-core aspects of the nodes on Summit, and ESMAX is exploiting the GPUs, and we can get those to be orchestrated and run concurrently. This is just a way of generating more throughput more effectively. So then we come to the kinds of scale we're looking at. This slide is relatively repetitive. It's just to note that the turnaround is, it's important to get answers in a hurry, to get lots of calculations done and iterations taking place. And in that sense, we've been able to take quite a lot of lead-looking compounds to experimentalists. And we do have quite a sizable number of interesting compounds now that are being evaluated. And indeed, one of my colleagues in London, who runs a Medical Research Council's clinical trials unit, just earlier this week invited me to start proposing some of the compounds that we've been uncovering for potential use in clinical trials. So that's something that brings us very close to an active medical project. Here's just sort of winding up and taking us to a different level. If you remember, certainly CompBiomed has a molecular level exemplar that I was discussing a lot. It runs across all scales, as I mentioned with the HIV instance, from the molecule to the whole human, the virtual human, and maybe beyond. This is an amusing example of what the state of the art is in kind of cardiac modeling today. So this is whole human heart modeling, where the methodologies are not molecular, of course, at all. They're based on a combination of things like solving bi-domain equations. There's fluid dynamics for the heart and the electromechanical response. So these are complicated models which themselves need to be run on pretty powerful machines. And they can be used to evaluate the cardiotoxicity of certain anti-malarial and antibiotic drugs that have cropped up quite a lot in the press, with some people, as you can see in this picture, telling us that they're going to be using some of these drugs. So what's happening in this project is that we use the ALIA code from Barcelona Supercomputing Center to assess the effects of those drugs on heart behavior in normal humans. So we have high fidelity human hearts. You can have a heart for a woman, you can have a heart for a man. You can ask what happens if I look at the nature of the beating heart when these models are subject to doses of those particular drugs. So hydroxychloroquine is a well-known case, the others are rather similar. And what's found here, and you can see, I hope, simulations, they're rather large files that are stacked into this slide, but they're dynamical simulations running ALIA with my colleagues Mariano Vazquez and Hasmin from the BSc, and they find that if you use large doses of chloroquine here, you can detect so-called left bundle branch blocks arising, which are things which are arrhythmias that mean that the left ventricle actually behaves in a slower way than the right, and pushed to the limit can cause serious sort of heart anomalies. And in the other case, which is for female hearts, with another one of the drugs that was looked at, they observed something called torsade de pointe, which is an arrhythmia that is extremely dangerous potentially and can lead to sudden cardiac death. So these are examples of the consequences you can arrive at if you foolishly take these kind of drugs without due attention. And the modeling and simulation is in a position to advise us prior to actually testing things out. So I probably overrun my time, but I'm just coming now to the conclusion here, and it's really about the outlook. I'm trying to make the point here that if we're going to advance medicine, we have to understand it in a more scientific way, not continually fund it to produce translational results at breakneck speed. And we need mechanisms to do that. That requires theory, modeling, and simulation in addition to experimental research. So basic research is necessary for this. And there's no way around it if you've got the complexity we have to deal with in these medical scenarios, that you're going to have to make use of the most advanced IT you can. It's an opportunity and a challenge, as I've said before, because the medical community is the one among the scientists, perhaps more than any, who don't really understand the importance of this kind of technology at the moment. The last point is, I think to really make these things work, you need major collaborations where you've got all pieces together, not just fragmentary things. It's hard to align them. And I think with that, I'm just going to close with the acknowledgements to a bunch of people who've been influential in working with me on this area and the funding agencies that have come to support us. I will now stop and thank you for your attention.
Thank you very much, Peter, for a truly thought-provoking talk. One of the things that I was thinking about when I was listening to you was the fact that it would be great to see a CCAM workshop organized in that area, and which also provides me with an opportunity to remind everybody that the call for this year's proposal is open and will be open until at least the 19th of July. So if anybody has ideas also in the framework of collaborations and collaborative efforts, or to encourage that kind of things, these are proposals that are certainly welcome at CCAM. So first of all, thank you to the three of you for three very, very interesting talks. We do have a few questions from the chat that I will now ask, but in the spirit of the informal discussions that we try to have always, if any of you has also a question for one of the other speakers, please feel free to ask it at the end of my first round of questions. So the first one is for Cecilia, and the question is, how much do you think that machine learning force fields are transferable across different protein models, for example?
That's a very good question, and there are different levels of answer, I think. The goal is to have transferable force field, of course, but depends what the interplay between accuracy and transferability is not always clear, especially at reduced resolutions. I mostly work with coarse-grained force field, and what is the resolution where you can achieve the best compromise between accuracy and transferability is not clear, is an open question. For the all-atom force field, there are some force fields available that have been trained on multiple molecules and have some transferability. There are some force fields that have been developed only for specific molecules. Most of the force fields at the atomic level that are available are for small molecules. There are people working on it, but at present, to the best of my knowledge, there is no available force field that is machine learned on protein data for proteins. We are working on it, other people are working on it, but I don't think for proteins there is anything available yet. But that's the goal.
Thank you very much, Cecilia. Ignacio, we have two questions on the all library. And the first one is all transferable across GPUs, or are there specific requirements for the type of systems or clusters where it can be used?
No, the idea, as I was explaining, is that to make it as transversal as possible. So in principle, it should be possible to use it on different type of GPUs, so it shouldn't be a problem.
And then building on that, transferability across type of systems is all effective also for systems in which the dynamics is spatially heterogeneous and where you have long range or many body interactions.
Okay, so that's a bit trickier, but that's because of the nature of the long-range interactions themselves. So I would need to check the details. My understanding is that it's mostly related to the intrinsic limitation of the method that one has to implement to deal with these long-range forces and on the library itself. But definitely there is a bottleneck. Yeah.
But if I remember correctly, there were developments related to lamps and the use of all-in lamps that also addressed that. But as you say, something to be further checked.
Exactly. So that's why I don't think that there is a general answer. Then it depends a bit on exactly the type of code, the way in which these long-range interactions are dealt with.
Yeah. So I have a question for Peter, because you said something that really intrigued me about how we should try to get to a point where we look at computers as a real resource also in medicine. And your example was the example of weather predictions and the fact that we have very complicated partial differential equations that we can't solve nowadays fast enough to make, to then decide if we want to use take the umbrella with us or not. So I guess my question is, how many equations do we have for something like, a human being? And because to me, the nature of modeling seems a bit different in these two extremes.
I think it's only a difference of a kind of quantity rather than quality in a way. You're asking an extrapolated question now about doing whole human simulations, I think.
No, I was asking, how far are we into the process of trying to even have a mathematical form for the questions that we want to ask in medicine? Okay. I mean, you showed some super interesting examples, and each one of them seemed to employ a different type of underlying mathematical structure. And so that in itself seems to be a huge challenge.
If you look at the cardiac modeling, the human heart modeling is the most sophisticated that there is at the level of organ systems development, right? And I showed you very high level view of the ALIA code. I mean, ALIA is actually a bigger code. This is ALIA red, there's ALIA gray. It even got mentioned in Dan Brown's book called Origin about people working on supercomputers in Barcelona and so on and so forth. But the code has been under development for, many, many years. And if you talk about the heart modeling components of that, there's a lot that's known there. There are things called bidomain equations. It's a multi-scale thing in the way that it's worked on. You have cell models that are like so-called Hodgkin-Huxley things. There's nothing below that at the molecular level in this. The lowest level are these cell models that display collective behavior for, the electrophysiology. There's the mechanical motion, there's fluid-solid interactions, and on top of that, there's fluid dynamics. But essentially, the physics of all of those things is understood. The challenge is putting it together as a multi-physics type application. It's got a kind of multi-scale element from the cell to the whole entity. But that does work now. The fact of the matter is, and that's very true for all cases, weather is not an exception. Environmental science, climate prediction, biological systems, and indeed the epidemiological one I mentioned, have something which makes them more challenging than the conventional science ones. And that is, they typically have huge numbers of parameters in them. And those parameters need to have values. And the question is often, how do I get those values? And if you were doing blind big data, which I'm extremely skeptical about, of course, there are people who do climatology who tell us that we don't need to run Navier-Stokes solutions. I just get the weather at this point, every day for this given day for the past 100 years, and I can predict the weather here tomorrow off that. And we know that doesn't work particularly well because we have things like curse of dimensionality, etc. But in the case, going back to the models, the number of parameters in them is such that we don't know for sure whether the data that we've got in them that are being used to fit them are doing a decent job. It's not a question in the so-called era of big data that we're actually flooded with it. We don't actually have enough data to really test these things as models as such. So that in the epidemiological model I referred to, it has 940 parameters in it. It's a very small model in some respect. How do we actually nail those parameters down? A lot of that has to do with proper measurements, experimental, and connecting to them, and being clear about how reliable they are. Because in the end, it's, you know, at the moment, these human heart models can largely distinguish between a human, a male and a female kind of thing, because there are major differences there. But then there are lots of other parameters in them that at this moment, people aren't sure about how to nail down to represent one individual completely. So those are big generic challenges, but they're not true only for biomedicine. They are with many areas of major societal importance today.
Thank you, Peter. So we have passed the 2 hours mark, but if any of you has a curiosity or a question for one of the other speakers, I think we should take the time to listen to it.
I had the curiosity also, I mean, it's building on this question. You were referring, I mean, you were describing now, Peter, the importance of having this modeling, but when you were setting up the stage, I was wondering, in the particular case of medicine, again, given the complexity of the system and how, I mean, how the speed at which an answer is required, how do you see the balance between doing this type of modeling and more data-driven approaches where you try to use machine learning or other type of schemes to really provide a faster answer? I don't know, how do you see these two legs or these two directions talking to each other?
Great question, and I may have failed in my haste to go through this to convince you that we, in the scenario that I gave with the consortium with the DOE labs, it's very much a combination of both. There's a huge amount of sort of machine learning type methodologies that are used to do docking or predict docking. They don't actually do it, but that then becomes very fast. It's what I call cheap and cheerful, because usually it's got a lot of uncertainties around it, which machine learners tend to forget to talk about. But it can come up with some kind of ranking. So that's what happens. We can run gazillions of these things, and then we have a meeting quite often every week. We look at the top 400 or 10,000 of these things, and those are the ones that they and we need to do more accurate calculations on. And we do those, and then we feed it back to this loop. And actually, in the hype and the funding agencies' obsession with bringing high-performance data analytics and H.P.C together, of course, machines that we're going to be seeing more and more of at the exascale, like Summit, and I mean, even Fugaku, they have code processors, and sometimes the machine learners are seen to be the ones who use the GPUs, and the H.P.C is less so on that. I think that's a false dichotomy. But the idea is these machines are meant to enable those things to happen. And I was sort of pointing at the fact that that's what is going on. We have these workflows where the two things can be running together. But the problem with machine learning can often be that it may make mistakes. And that's why I insist on the importance, as you may know from a paper I wrote a few years ago, it's called Big Data Need Big Theory Too. If you just do big data analysis without paying attention to the structural characteristics of the problem, you're liable to come up with some very foolish predictions. So I think it's essential that the two are kept in play together, not to just say we'll solve this by the black box that can get the answers much faster.
Okay, so I think we are coming to the end of another very interesting, at least for me, CCAM webinar. So let me thank again all our speakers, Cecilia, Peter, and Ignacio. And I would like to thank all of you who have kept us company on the YouTube channel, and give you an appointment for next week when we're going to have the 4th installment of the CCAM webinar series, The Importance of Being H.P.C Earnest. Thank you very much, and see you next week. Bye.
Thank you. Bye.
Thank you.